So if you want to find the second order polynomial for a function of two variables, you're going to do it in a very similar way to how you would find it for one variable. So let's look at the first order formula. You see that it looks very similar to the formula at the top, where you take the original value of the function and you add the change over the distance that it changes. And it looks very similar if you just ignore this part, because these are higher orders, so you have like a 2, a 3, and so on until you get to n in the exponents, but you aren't going to have that down here because this is just a first order, so the only exponent you'll have is a 1. Other than that, the major difference is that you have to break apart this derivative into the partial derivatives. And you have to make sure that if you're writing the partial of x, you're multiplying that by how x changes, or the distance over x changes. And for the partial with respect to y, you have to make sure that you're multiplying it by the distance that y changes. So when we get to the second degree, things become a little bit more complicated. So the first part is just the first order derivative, but then you have to keep adding, like you do up here, the second order derivative over n times the distance squared, and you keep going until you get to n, but in this case we just stop at 2 because n is 2. So here looks pretty similar to up here. You take the second derivative and you divide it by 2, and you have the 2 in the exponent, and this part also looks pretty standard because you're taking the second derivative of y, or the partial of y, but this part of the formula is pretty different, and there's nothing like it up here for the one variable formula. And that is because you have to take into account that not only is f double prime of x and double prime of y changing, or not only are they making the function change, but also the fact that, that should be next, the fact that fxy and fyx are also, if they are non-zero, then they're also contributing to the overall z value of the function changing. So you have to write them in the equation as well. So the 1/2 is the same as here when you have to divide by n factorial, and then you multiply by the derivative, or the nth derivative, so it's still the second derivative, but it's just the second derivative of x with respect to y. And instead of having an x minus a squared or a y minus b squared, you just have x minus a and y minus b, because you aren't taking the derivative with respect to the same variable. So because you're noticing how the function changes with respect to x, you have to multiply that by the distance over which it changes, and the same is true with y. After you get f of x sub y, you have to do f of y sub x. But if you remember, the two are equal. So instead of writing it out as half of this plus 1/2 of this expression, you can just write it as 1 times, then you can either pick f of xy or f of yx, it doesn't matter because they're equal. and write it like this. So that is where this comes from. It comes from the second derivatives that that have two different variables in them.